Hyman, and I was also on the site. And so presentation we got was on the entire standard model. We only really focused in the lab that I worked in on the strong force and its interactions. And because we sort of called strong force the color force, really just out of convenience, we call it quantum chromodynamics, which sounds cool. Alright, so these are the matter particles we work with, the quarks. And you can see the three generations of them again, heaviest to lightest. Little fun trivia fact, if you want to know where the name comes from, it's a line in Finnegan's Wake, and Murray Gell-Mann, the scientist who first proposed the existence of quarks, thought it was real clever and named them quarks after that. And the force carrier we're looking at, again, is the blue one. Figured I'd remind everyone. So, let's go into a brief history of how they came up. Again, Murray Gell-Mann. So, back in the 60s, when they were looking at sort of what was the standard model at the time, there were so many particles that didn't seem to really have any sense made out of them, but Murray Gell-Mann realized that if there were these three constituent pieces that he called quarks, you could classify them in the scheme that he made based on strangeness, which I'll explain later, it's one of the quantum numbers, and their electric charge. And he called this classification the eightfold way. And because of it, he was able to postulate the existence of quarks. Later on in the 70s, the color charge was introduced, and quantum chromodynamics was born. So, what is it? It's the theory of how the strong interaction and the quarks work together so that all hadronic matter, all quark-bound states, are completely confined within a hadron. And the way it works, as Omar did talk about a fair bit, is that all quarks have a colored charge, which is just called color because it needs to be neutral. And we know that red, green, and blue light together is white, or anti-red, anti-green, anti-blue. There's no actual color going on, don't let that confuse you, it's just called that. And so you can have 3 or 2 quarks in a bound state. Either 3 quarks, which is a baryon, and have red, green, and blue charge, or anti-red, anti-green, anti-blue, like here. Or a meson, which is 2 quarks in a bound state, and then you have a color and an anti-color. But it always has to be color neutral, which is because of color confinement, which I'll get into right after I explain this, which is just that the strong force is actually visible in multiple ways. I won't really be talking about the residual nuclear force, but if you were remiss if I didn't mention it. It's the force that is created by nucleons, like protons, neutrons, going together that in chemistry. They exchange the color neutral pions, and pions are also mesons, in order to interact, and it works on about 1 to 3 femtometers. It's not a big deal in this particular presentation. And then the one that we were really looking at is the strong nuclear force, which confines quarks. And this force it interacts with quarks by the quarks exchanging color and anti-color gluons. And it works on about less than 0.8 femtometers, which is very small ranges. And you'll see why it has to be so small because of color confinement, which has to do with this. If you think about gravity, as you know, maybe from physics, as you move 2 bodies apart, the strength of the force decreases with the square of the distance. So as you get farther away, it's getting smaller much faster. However, with the strong force, if you try to separate color-confined quarks in a bound state, you have to continually put the same amount of force in to move them. The force doesn't drop off exponentially, it drops off linearly. So what happens is, let's say you put a ton of energy into this blue up quark within this proton right here, in order to try to separate it from the baryon. What you'll do is you'll pull it apart gradually, but as you start putting that much energy into it, you'll have created enough energy that instead of just breaking it off alone, you'll have enough energy to break it off, and from the vacuum, spontaneously create these mesons. And they'll be color neutral by definition, but they'll also be canceled like up and anti-up, down, anti-down by their antiparticles. And as you'll see, you still have the original baryon, just with a different quark, the same color and same type. That's a little confusing. Should I pause here and see if anyone have any questions? We're good? All right, onward. That's color confinement. So in the simple quark model, there are these two types of hadrons. There are mesons, which are always quark, anti-quark, so the color and the anticolor, like blue, anti-blue. And there are baryons, which are just quark, quark, quark. So either red, green, blue, red, anti-green, anti-blue. It's a little redundant, but that's not technically the only thing that quantum chromodynamics would allow. All the rules state is that these states have to be color neutral. So theoretically, you could have a pentaquark, which has these 5, as long, if you have a color neutral baryon and a color neutral meson, there's no rule in quantum chromodynamics that says that they can't be bound together in a huge 5-quark state as long as it's color neutral. And these states are called exotic bound states, and they've yet to really be observed in experiment. So the way that we sort of arrange, or the way that quantum chromodynamics created these rules was sort of through the scheme that I mentioned earlier, the eightfold way, which is Gell-Mann's system for organizing hadrons. And it's organized in 2 ways. The electric charge, which is either positive 2/3 or negative 1/3 for each quark. And strangeness, which is the number of strange quarks, or the negative number of strange quarks minus the number of anti-strange quarks in a bound state. So this is a little bit easier to see. So what you have is these organized like systems or triangles for the quarks and the antiquarks. And what you'll see is for the quarks you'll have strange down and up, and then organized along the horizontal or the diagonal axes, you'll see that the charge is increasing. And for the antiquarks, it's anti-up, anti-strange, anti-down. So in order to create what should be allowed within the quark model, what Gell-Mann proposed is, and was correct about, that if these are sort of the, if you take these constituents and line them up so that they're centered, centered around this point, and this point, then the places where the new intersections are created are where you're going to have the overlap in types of quark. That's really hard to picture. Let's look at the other one, actually. Let's look at the mesons quickly. So what I'm saying is, the way that he did this, you would center this triangle, or imagine that there were 3 points here, here, and here for that first sort of triangle group. You would center these triangles around those points and be able to come up with this octet. And then, slightly more complicated for the baryons, since there are 3, you just have the same process occur again over that original octet, and you'd come up with this non-net. So that's, and you theoretically continue doing that until you add bigger and bigger particles, so like pentaquarks or other bound states. So those like higher levels other than mesons and baryons would be the exotic bound states. So that's pretty exciting, because that's a new frontier in physics. That's what we can look for next. Bound states that we haven't yet seen, but theoretically should be possible. And there are a couple of places that have been looking for it. The lab we're working in is part of a huge collaboration that is called the Blue X experiment, looking for exotic bound states of quarks. And But there's also experiments at CERN, Japan, COSI, there are many, and Alden will get into that a little more. He's talking about experimental methods. So now, I'm sure there are any questions. Yeah, of course.
Well, I'm not exactly an expert in physics, but what is the material that you're testing for? What is this?
Physical. It is physical because you're made out of mostly it.
Yes.
So, if you remember the baryons, 3 quark states, those are the protons and neutrons.
Oh.
So yeah, they're constituents of most matter that we deal with on a daily basis. But it's the smaller, more fundamental bits of them that we're looking at. Does that help? Yes.
Can you explain strangeness again?
Yeah, strangeness is just, it really just has to do with how many strange quarks and how many anti-strange quarks there are in a hadron. It's literally just the definition of it. It's just that numerical value. If you take the number of strange quarks in the system and subtract the number of anti-strange quarks, you take the negative version of that, the strangeness. So the reason it was used instead of like color or something is because the color of a quark is able to change. If it emits a gluon, then its color does change. So it's not something that's really inherent to a quark, but its strangeness is the quantum number that has to be conserved. So if you organize by strangeness, then you won't run into as many problems with having continuously changing systems all the time. Sorry. Sorry, that didn't help at all. Yeah.
How do you pull these sets apart?
Pull set? You mean the hadrons? Yeah.
Yes.
So actually, Alden's going to talk about that a little more, but as all things with particle physics, it's pretty much just shooting energy at them. But he'll explain it more. Okay.